Artificial intelligence and machine learning have evolved from theoretical constructs into transformative technologies shaping organizational strategy, public services, and everyday life. Artificial intelligence refers to computational systems capable of simulating aspects of human cognition, including reasoning, pattern recognition, and decision-making. Machine learning, as a dynamic subset of artificial intelligence, enables systems to improve performance through exposure to data rather than explicit programming. Together, they function as central drivers of digital transformation, particularly in environments where efficiency and innovation are constrained by limited resources. Although technical scholarship has extensively examined algorithmic design and computational architecture, the broader socio-economic implications of artificial intelligence and machine learning demand equal attention. Their relevance is especially pronounced in resource-constrained contexts, where technological leverage can produce disproportionate impact. Applications in agriculture, financial inclusion, and personalized education demonstrate that artificial intelligence operates not only as a technical advancement, but as a structural mechanism reshaping access, opportunity, and institutional capacity. The historical evolution of artificial intelligence can be traced to mid-20th century conceptual breakthroughs. Early theorists proposed that machines could simulate intelligent behavior, laying the intellectual foundation for computational experimentation. Initial programs demonstrated rudimentary capabilities in natural language processing and symbolic reasoning, signaling the feasibility of machine cognition. By the 1980s, expert systems embedded rule-based logic into specialized domains, marking one of the first large-scale integrations of artificial intelligence into organizational practice. The 1990s witnessed significant expansion in machine learning methodologies, including advances in neural networks and statistical modeling. As computational capacity increased and digital data volumes expanded in the early 21st century, deep learning emerged as a transformative development. Multi-layered neural architectures enabled breakthroughs in image recognition, speech processing, and automated translation. By the 2000s, artificial intelligence and machine learning had become embedded in mainstream technologies, ranging from autonomous vehicles to predictive analytics platforms. At the conceptual core of machine learning are algorithms and models. Algorithms consist of structured computational instructions designed to analyze inputs and generate predictive or classificatory outputs. Approaches such as decision trees, support vector machines, and neural networks represent distinct strategies for identifying patterns within data. Models are refined through iterative training processes in which internal parameters are adjusted to reduce error and improve accuracy. Data functions as the foundational driver of artificial intelligence performance. Structured data, including numerical records and unstructured data, such as text, images, and audio, provide the material through which models detect patterns and generate predictions. The quality, representativeness, and governance of data directly shape outcomes. Inaccurate or biased datasets can distort results, reinforcing inequalities or producing unreliable decisions. Data governance therefore emerges as a central dimension of responsible artificial intelligence deployment. Neural networks draw conceptual inspiration from biological brain structures. They consist of interconnected layers of computational nodes that transform data through weighted relationships. Deep learning extends this architecture by incorporating multiple hidden layers capable of identifying complex and hierarchical patterns. This structure underpins contemporary applications in computer vision, speech recognition, and natural language processing. The effectiveness of these systems derives not only from computational scale, but from their capacity to learn progressively refined representations of information. Effective adoption of artificial intelligence requires deliberate implementation pathways. Pilot projects targeting narrowly defined challenges enable organizations to test feasibility, assess risks, and evaluate impact before scaling. Open-source frameworks offer accessible entry points, while structured training initiatives cultivate local expertise and institutional sustainability. Implementation thus involves organizational learning and capacity building alongside technical deployment. Applications across sectors illustrate both transformative potential and structural implications. In healthcare, algorithmic diagnostics analyze medical imagery and clinical data to support early disease detection and treatment planning. In agriculture, predictive models optimize irrigation, forecast yields, and detect pest patterns, enhancing productivity in environmentally uncertain regions. In financial inclusion, machine learning-driven credit scoring analyzes alternative data to expand access to microfinance for populations without formal credit histories. In education, adaptive systems personalize content delivery according to learner profiles, addressing disparities in access and engagement. These applications demonstrate that artificial intelligence can advance efficiency and equity when implemented responsibly. Yet opportunities are accompanied by significant risks. Biased datasets may replicate existing inequalities, while opaque decision-making processes can undermine transparency and accountability. Privacy concerns intensify in contexts where regulatory safeguards are weak or enforcement capacity is limited. Organizations operating in developing or resource-constrained environments face additional challenges, including limited digital infrastructure and insufficient technical expertise. Strategic partnerships with academic institutions and technology firms, investment in local training, and careful selection of scalable tools can mitigate these barriers. Equally important is embedding ethical principles, fairness, transparency, and inclusivity within governance structures to prevent technological innovation from generating new forms of exclusion. Artificial intelligence and machine learning are no longer peripheral innovations. They constitute central drivers of organizational and societal transformation. Their effectiveness depends not only on computational sophistication, but also on ethical stewardship, contextual adaptation, and sustained capacity development. Integration across healthcare, agriculture, finance, and education underscores their potential to support inclusive development in low-resource settings. Future inquiry must continue to examine the intersection of artificial intelligence with governance, equity, and sustainability. Responsible deployment requires balancing innovation with accountability and experimentation with regulation. When guided by ethical governance and collaborative capacity building, artificial intelligence and machine learning can function as catalysts for equitable development rather than mechanisms that deepen structural divides.